So our next speaker is Daniel Clarke. He's a security architect with Schneider Electric, and he is going to be talking about Secure Modbus. I just love that. Secure Modbus with role-based authorization. Please welcome Daniel.
Okay. Here we are. Okay. So, thank you, everybody. Welcome to our idea for Secure Modbus. As many of us know, Modbus was invented about 20 years ago by a company called Modicon, which became part of Schneider Electric. And thanks to its simplicity, Modbus became one of the most widely used protocols in manufacturing environments. And today, it's implemented by hundreds of different vendors, and it's on thousands of devices. And the main use of Modbus is to exchange data between different parts of the industrial process, between PLCs and devices, but also between PLCs and SCADAs. And what's been missing from Modbus up until now has been the security. So in Schneider Electric, we've been working on ways that we can add security into the Modbus protocol, but without breaking the simplicity which has made Modbus so important in the first place. And while retaining the simplicity, we also have to make sure that we retain the compatibility. We don't want to break the large ecosystem which is present. And we also have to do it in a way that lets people adopt Secure Modbus in a progressive manner. It's not an all or nothing proposition. We can prioritize the data flows that are most at risk and do the other data flows in a later step. So this is where Modbus gets used. On the right-hand side, we see a process diagram. On the left-hand side, the control infrastructure. And inside the process, in this example, we have sensors. We have, like, for example, pressure sensors. We have pumps, which are used to move the liquids around. We have tanks, and we have valves. And these physical elements are sending information back to the PLCs using Modbus, and the PLC is then pushing that information up to SCADA. So we can imagine there are some things that can go wrong here. Like if a PLC thinks that the pressure is low when actually it's high, then that could result in the PLC sending an inappropriate command to one of the valves. If the operator at the SCADA console, he has visibility of the process and what he's seeing is not actually reflected in the physical state, then we can imagine problems will also result. And when we try to add security into this, we're going to see there's going to be some changes. And the main change that we see here is we have a new function in the supervisory layer of the network. This is the PKI function. This is going to play a big part in the commissioning of plants. Now, what we have to be careful about is this is not changing the operations of the plant. It's part of the setup. If we want devices to do secure protocols, we have to be able to give devices secure identities. And today, when we do commissioning, we configure the devices, we give them a program, we set up the data flows that they participate in. When we do secure industrial communications, this will be the same, but there'll be an extra element in that commissioning, which is its secure identity. And all of the elements in the system that want to do secure communications will figure in that step. And once we do that step, what it enables us to do is to have these secure data flows. So where previously there was normal Modbus with very little security, we have Secure Modbus, and we're going to show what that means. So firstly, the dangers, like when we do have these insecure protocols in our industrial process, we have situations where operators might not really know what's going on in the process. This could result in damage to equipment, maybe some danger for the people on the factory floor, or economic costs like downtime and unusable output. And obviously these are not things that get accepted, and people deploy countermeasures, additional layers of security like network segmentations and firewalls. And these are all good things that we're going to retain. But by having protocols with native security features, we get extra security value from these layers, and we get an additional layer of protection. And what we have to start with is like just a robust protocol, something that's resistant to replay. It's resistant to man in the middle, and it doesn't allow for downgrading. There's not going to be a way to strip the security off the protocol. But we're also going to need the authentication. PLCs have to know what they're talking to. They have to know that the pressure sensor that they think they're reading is the real pressure sensor, and that the information that's getting sent back is protected for integrity. It can't be modified on the wire. There's also got to be a concept of authorization. This is missing from Modbus now. And what authorization does is it gives us containment. If something is compromised on the network, it can only damage things that it's supposed to be talking to anyway. It can't start sending commands around a plant. And we can do encryption if we think it's needed. It's a lot of the time it's not needed. Like these pressure readings and commands are not particularly confidential, but if a user wants to do it, they can. And so this is what we're looking for in a protocol, and the way we want to do it is by using the best practices and taking something that we know works. And what works in IT is TLS. We all know this already. TLS is the S in HTTPS. And it's trusted by the major IT players. This is what the Microsofts, the Googles, the Amazons are using. It's what's used to secure online banking and e-commerce. It's an internet standard. And it's an evolving standard. TLS started out about 20 years ago, and it's been through a significant number of revisions. A lot of people are looking at this, very smart people, and they're finding problems with it. But the problems, they get addressed. And sometimes in the early years, there were mostly protocol problems, like these were security holes at the actual protocol level. And new versions of TLS were created to counter this. Today, we sometimes get bugs in implementations, like some of the high-profile OpenSSL bugs, but they also get found and they get corrected. So by leveraging this, we can take what works, and we don't have to reinvent the wheel. And our problem becomes, how do we combine this with Modbus? Now, the good news here is that TLS can protect any TCP-based protocol just by encapsulating it. And what that will already gives us is the foundation of communication security. We'll get mitigation for replay, we'll get mitigation for man in the middle, and we'll get integrity protection. And if we want to have authentication, we'll have to do a bit more, and we'll see how that will work. But the other important thing from TLS is we get cryptographic agility. So we all know that the algorithms improve over time, the attacks improve over time. TLS has a built-in mechanism of cipher suites where the two endpoints, they negotiate what security algorithms they want to use, what key sizes they want to use. And these algorithms can actually change without changing the underlying protocol. So by using TLS for Secure Modbus, we get that level of flexibility and future-proof. In terms of how this will change how Modbus looks on the wire, so for Modbus TCP, which is what we're all familiar with, it's a very straightforward encapsulation of Modbus in the TCP data structure. The unprotected Modbus data, it goes into the TCP payload, and there's just a checksum value which protects against errors. When we go to Secure Modbus, that picture does change a little bit, because the application data that goes in the TCP packet, it also has to contain TLS data. So the packets will look a little bit different. The good news is to the application, to the Modbus protocol handler, that's actually transparent. The only difference to the protocol handler is that instead of it doing a TCP reader write, it's doing a TLS reader write. And the management of this TLS metadata that goes around the Modbus data is completely transparent. So it's a very minor code change inside the protocol handler. And if we look at how that integrity protection actually works, this is, so one thing to know is TLS has a lot of different modes. There's a mode of TLS which it can be with no authentication, server authentication, mutual authentication. What we want to do in Secure Modbus is mutual authentication. The PLC has to know which device it's talking to, but the device also has to know which PLC it's talking to, because an attacker shouldn't be able to spoof either of those endpoints. When we do this, the integrity protection property is coming from this message authentication code value, which is here. During the TLS setup phase, a number of keys get negotiated, and one of these keys is a MAC key. So it's a secret value. It's known to the two endpoints, but it's not known to anybody who observes the setup procedure. And this MAC is a calculation using a cryptographic digest. It's using like SHA-2, and it's combined with this secret key. And the digest, it covers the sequence number, and it covers the Modbus data. So when the receiver, it gets that message, it performs the reverse calculation, and it checks, does this correspond with the MAC in the message? An attacker who tries to change that data, he won't succeed, because he doesn't know the MAC key. If he changes the Modbus data, the digest will give a different value, and the MAC won't validate. The receiver can detect it. In addition, the attacker is not able to inject an old message, because we can see that the MAC value, it includes the sequence number. So if a receiver, he sees the same sequence number more than once, he can reject it as a duplicate message. If we did have encryption enabled, it would work in a similar way. The payload, the Modbus payload, will be encrypted inside the TLS record instead of just being integrity protected. Otherwise, it's the same idea. When we talked about mutual authentication, this is what we meant. At an earlier point, we mentioned that we were giving every element of the control system a secure identity. This secure identity is an X509 certificate. And what the certificate does is it's a binding of a name to a public key. So when you present your certificate to somebody, that person, he knows who you are, and he knows what your public key is. And that's attested to by the PKI function, which is a trusted function on our network. Each of the endpoints, they verify each other's certificates, so the PLC knows exactly what it's talking to. And the way that works in the TLS handshake procedure is there's a number of messages that get exchanged. The client who wants to open the connection, he starts by saying hello and sending some random numbers. The server, he'll send back some other random numbers. The client, he will verify the server certificate. And he will also do, there's some cryptography at this part where the client, he chooses an additional random number and he encrypts it with the server public key. And this is important for two reasons. It's important because the servers are actually fan-in points, so you don't want the server to start doing work before the client does work, because it could lead to like a denial of service attack. And it's also important because an attacker who's observing this communication, he doesn't know what that pre-master secret is. And because he doesn't know that, at a later step, he's not able to determine what the master secret is, and that's what derives the keys which give us this communication security. And once this connection is set up, the two endpoints are able to exchange secure Modbus as they would be today with normal Modbus, except that Modbus is now protected. For authorization, we have the problem that the Modbus protocol, it does not have any provision to transmit a role. And we're not able to change the Modbus protocol, because if we do that, then all of the existing Modbus systems, they would no longer, we would have incompatibility. So what there is inside of the X509 certificates, which we need for secure identity anyway, there's an extension mechanism. And we've registered an OID to allow us to encode the industrial role into the extension attributes of X509. So as long as the different vendors of Secure Modbus, we have a convention, we use this OID to transmit the role around the system, we're able to get this property of containment. And the TLS handshake process actually provides for a place where this can be checked. And it's a multi-level check. The first level can be, is this endpoint supposed to connect to me? And we can already do something there. A second level can be, is this endpoint supposed to be sending me this type of Modbus? And that would be in the protocol handler. When we want to talk about interoperability with existing Modbus devices. So Modbus, it's on port 502, and we know that there's already a large number of devices out there with different ages, and we're not sure we can update all of them. So the last thing what we want to do is to start sending TLS handshakes to these devices, because at least in some cases, the behavior could be unpredictable. So what we've done is we've registered a new port for Secure Modbus. It's port 802, and it's reserved with IANA. So as long as everybody uses this port number for Secure Modbus, we'll get the same interoperability between vendors of devices enabled for Secure Modbus that we enjoy today with normal Modbus. So up until now, we've talked a lot about certificates and the role they play in Secure Modbus, but we haven't said very much about where these certificates are going to come from. And what we have to do in order to get these certificates is enrollment. So devices in their commissioning phase, they will need to generate this public-private key pair. The private key has to be generated on the device because it's important that it's only the endpoint that knows what it is. But in order to get the certificate, we've got to send the public key and the identity to this PKI function that we've put on the network. And inside that PKI, there's got to be a verification of that identity. Is this something that's supposed to be in my control system? And that verification, it can be based on a MAC address, it could be based on any other decision, but it's got to be present. We can't just let anything have a certificate, because otherwise the attacker also will be able to get a certificate. And once that verification is satisfied, then a certificate will be issued and it will be pushed back to the device. But this is only one side of the problem, because once we have these certificates, we need a way to determine certificate status, because devices will have lifetimes. And once a device is taken out of service, it's still got this certificate in its memory somewhere, unless it's like disposed of in a very safe way. So we need a way for the other elements of the system to know that that certificate, while it does have a valid signature, while it is within its validity period, that it should no longer be accepted for secure communications. And the way this has worked in PKI has been to have certificate revocation lists, which are maintained by the PKI. And as certificates are invalidated, they're entered onto this list. And this list is not without problems, because it can grow to be quite long. And that can be cumbersome, and we don't necessarily want industrial devices dealing with that all the time. But the good news is this is also a problem that was faced in the IT world. And in IT, there's been a number of developments, like OCSP has been around for a long time, which it's a way to, instead of dealing with these CRL objects, you can say to a server, tell me, is this certificate valid? And this is a simpler approach, but we still have a situation where we don't want devices, as they receive connections, to have to go off talking to another server in order to say yes or no. So what's becoming popular in browser world now is like to do this, but to do it in the other direction, where we put the obligation on the client to obtain their certificate status in advance and to staple that certificate status onto the connection request. And the endpoint can trust that certificate status because it's signed in the same way that everything else is signed. So these are some of the different options, and depending on the exact scenario, there will be different constraints, and sometimes one or other option will work better. But based on these options, we have some valid approaches to that problem. We also get interesting possibilities when we start to have PKI-based solutions. So we're in a world where companies collaborate together, and each company will want to manage their own trust, because that's a core part of their business. So if we imagine like a pipeline scenario, which is we have some major infrastructure, one company could own the pumps, another company could own the actual pipes, a further company a refinery, but all of their assets have to be able to interoperate in order to make the gas flow. So how can one of their assets trust an asset from a different company? And what PKI lets us do is that one of the companies can cross-certify the root of trust of another company, and automatically what's trusted in the other company's infrastructure is trusted in your infrastructure. And that cross certificate can be maintained for as long as the business relationship is there. So it gives us a very flexible way to address this kind of a problem. So when we start to think about the performance of this, we can expect to have some changes, but primarily at the connection setup time. Because when we're doing TLS or indeed anything with public key cryptography, the public key operations are what is computationally intensive. So we know there will be some extra computational overhead at connection setup. But the good news is that for the actual session data, these are linear algorithms, and there's not a huge amount of data which needs to be exchanged. So during the actual session data, the exchange of Secure Modbus compared to Modbus, there will be a marginal performance cost. And in addition to this, we have ways to manage this performance question in that we don't have to migrate every data flow from Modbus to Secure Modbus. We can choose the high-risk data flows and migrate only those. And if that keeps us within the performance constraint of the device, then we can stop there. And this is a constraint that will get smaller over time, because as we all know, the capacity of these devices is improving all the time. We're getting more and more native crypto accelerators. So, it might be a concern today because we have a mix of these older and newer devices, but over time, this concern will evaporate. In terms of how we can make this available and when we can make it available, so today we're working on this with some of the bigger Modbus vendors, and we're moving to create a final proposal that we can bring to Modbus organization. And we hope that after that we can make it available to the community. So this is where we are with the Secure Modbus idea. So at the outset, we identified we had a number of things we wanted to make sure we could do. So we had the authentication, authorization, definitely integrity protection, and we wanted to have to make sure that we had a good way to ensure compatibility with legacy Modbus and across different vendors. And we've seen how we can do this with the new port number and the X509 extension based on a standard OID that's registered. And we've also seen we have ways to do migration in that we're not obliging the use of Secure Modbus doesn't exclude normal Modbus. People can do this in a step-by-step way. So that's where we are. If anybody has any questions, we're happy to try to answer them.
Sure. Okay, so we'll go to question and answer. Please introduce yourself.
Hi, this is Rich Corrigan with San Diego Gas and Electric. I work for a utility. The majority of our SCADA signaling is done over serial communications. How would this work in that kind of environment?
Yeah, so the parts where we're using TLS would be between the PLC and the serial gateway. And the part where we do authorization, it could be a function on the serial gateway where the serial gateway is able to tell what sort of roles and what sort of identities are supposed to be able to bridge from that Ethernet to the serial and make a decision as to whether to allow that traffic to go forward or to just drop it. Does that answer the question?
Sort of. We don't use PLCs.
Okay. But you're going to have like the Secure Modbus endpoints, and the concept will be the same. The main thing is that we have this Ethernet to serial gateway, which has the capacity to firstly to be a Secure Modbus endpoint, and secondly to enforce that authorization decision as to whether it will convert from Ethernet onto serial.
We have to comply with NERC CIP.
Yeah.
And as soon as we put IP in the communications path, it's known as a external routable communications.
Okay.
And it opens up a whole lot of NERC CIP requirements then that we have to meet. So we try to avoid that.
Okay, that's interesting. So we have focused on the TCP part of this. The same protection architecture, it could work outside of a TCP as long as there's a transport which provides the primitives which TLS needs. So it'd be interesting to discuss that further.
Other questions? A quick one. You had that kind of timeline showing the things that have to happen. Do you have any sort of target date for submitting this to modbus.org?
So I don't. I think it's something that we would want to move as quickly as possible, but we're working with partners, with like the major Modbus vendors, to make sure that it's something that everybody is happy with. So it's important to finalize the proposal and then to bring it to modbus.org.
Okay, and I guess another question, okay, there's one over here, but while I'm walking over there, OPC-UA struggled with this issue of secure by default or just always work and let them secure it later. So in their case with certificates, the default is typically accept any certificate you're presented, regardless of any certificate authority. You just basically accept it, and then you have to actually make changes from that default to add security. Are you going to be proposing something like that to Modbus, or are you going to propose, no, you actually have to have a CA in place and be able to validate the certificate?
Well, I think the ability to do secure Modbus, it just requires you to have a certificate. And like the architectures we're preparing, they have this PKI function on the network. If a different vendor or user wants to do it in a different way, that, as long as the certificate is there and they're conscious of the risk that they're taking, then, it's their choice. But what it's also possible to do is to have a downgraded version of authorization. So you can say that on the endpoints, okay, the connection's been established, your certificate's validated, it changed back to a root of trust, I know, but there's something funky about it, so I'm downgrading what you can normally do. So from now you can only do read operations. You can't do write operations. So we can have a multi-leveled approach to dealing with some of the edge cases in these scenarios.
Yeah, I guess what we always worry about is a false sense of security.
Yeah.
So you could, like, if you have an OPC UA set up and each side creates a self-signed certificate, and then they exchange these and they think, oh, now I've got authentication, authorization, encryption. Well, basically you have no idea who you're talking to because you'll accept any certificate as valid. But on the flip side of that, they said, well, if we don't do that, a lot of people are going to plug this thing in and it's just not going to work because they don't understand how to put in a CA and an architecture. So it's kind of that balance,
sure.
and what you propose as kind of the default. Do you start secure and say you can make it less secure, or do you start less secure and require them to up the ante?
Yeah, and I think as well there'd be because if you are doing self-signed certificates, so firstly, we need to make it visible that isn't authentication. But it's also going to be probably more expensive than doing a proper certificate hierarchy, a proper PKI function, because every self-signed certificate is in effect its own root of trust. So the organization is going to end up dealing with the number of trust relationships will be the number of assets squared, and every asset's going to have to be configured with this different root of trust. So it will get messy pretty fast, I think, for a company that does that. Maybe on a very small scale it can work, but.
Okay. There was a question over here.
Parnia Najafi from FireEye. So with the new protocol, are you planning to give some recommendations so that they can change the hardware in a way that they can keep the private key secure as well?
Well, so we're not going to be telling other vendors how to make their products, and we have our architectures for how we protect private keys, and we presented on that on S4 about 6 months ago as well. So it's things that we share, but it's up to other vendors to decide what they want to use, and we'll do it the ways that we're satisfied that our hardware meets our security requirements. And does that help? Does that answer? Yeah. Yeah, it's not an appropriate use of public-private keys if you have no security whatsoever for your private key. So they should be doing, and they shouldn't be making claims which aren't appropriate either. Like, we have the security levels of 62443, so a device which is doing very basic security for its private keys, that should be visible based on the security device the security level that device is claiming. So something that that has like hardware key security will be able to claim like an SL3, whereas something that doesn't might only be, you know, a lot lower than that. Okay.
Yeah, Matt Cowell with Ultra 3 ETI. You explained the situation for a greenfield site, you know, brand new configurations. Everything's going to be the initialization, or the keys are going to be handled at the very configuration. Can you walk through, in reality, there's going to be some brownfield installations where it's going to be a hybrid of as they migrate to a secure Modbus with the existing. Yeah. Can you talk about the coexistence aspect and how you envision those two mechanisms will work?
Sure. So so we'd expect that there'll be some kind of an analysis that, you know, the owner of that infrastructure, they will know where their risks are, and they'll be able to prioritize which data flows that they want to move to secure Modbus first. Then they'll have they'll have a number of choices about how to go about it. Like they could try to separate it based onto different network controllers on the backplane of a PLC, or they could leave everything as it is today and just enforce it via some kind of a whitelist on the PLC that would stop, you know, downgrading of a data flow that's supposed to be secure Modbus down to normal Modbus. The fact that they're both TCP protocols and the difference is a different port number, it doesn't create a problem to have them both on the same network at the same time.